Welcome, ladies and gentlemen, and everyone in between and not on the spectrum, to the ICRAR Astro 3D Weekly Astro Talk. The ICRAR, of course, is the International Centre for Radio Astronomy Research across Curtin University and the University of Western Australia. We're also part of Astro 3D, the ARC Centre of Excellence in All-Sky Astrophysics, unifying over 200 world-leading astronomers to understanding the evolution of matter, light, and the elements from Big Bang to the present day. But first things first, I would like to acknowledge the traditional custodians of the land on which we're speaking, the Whadjuk Noongar land, and pay our respects to elders past, present, and emerging. Now, tonight, our guest is Dr. Luke Davies. Dr. Luke, how are you?
I'm very good, Greg. How are you?
Good. Thank you for joining us. It's fantastic to have you on. And
nice to be here with you,
talking about today, what are you going to thrill us with?
Well, I'm going to be talking about a kind of rundown of some of the things that I personally think make astronomy amazing. It's kind of a mishmash of things that are pretty cool about astronomy, just things that I think are good and are worth sharing with people.
Brilliant. I'm very excited to hear this. Now, before we go into that, we really have to ask the question, is it science or is it art? Because a lot of the time in scientific papers, there's a lot of plots and images that look beautiful, regardless of regardless of the science behind them. So we're going to have a look at a picture. I do believe there it is. And now, Dr. Luke and all of our wonderful people who are watching, what do you think this might be? It's something from a scientific paper, but what do you think it might actually come from? Any ideas?
I can chime in with the fact that I have absolutely no idea at all, Greg. So I can't help you in any way.
And neither do I, because this is something
we're both as ignorant as each other, Greg. It's nice to know.
We're just going to stand here for hours going, I have no idea. I don't know what's going on.
Yeah, no, it's just like day-to-day work, isn't it?
And so what we do at ICRAR on the ICRAR Twitter channel at ICRAR, so at ICRAR, you'll find this picture and you can make your guesses. And on Friday, we'll be telling you what it actually is. But looking at it, I think it's sort of got roundy bits, it's got sort of fractally bits, and it's an interesting one. I'm going to guess that it's some kind of, it's like signals or something like that, like the extent of signals. That's what I think it is. But
I'm going to guess it's a diffraction pattern of light through some.
Ooh, I like that idea. There you go. That's an exciting one too. Okay, so we have no idea what it is. We're both stumped. So, interesting idea.
We need someone to help us out, basically, and tell us what it is.
And our wonderful Kirsten, who is running the chat tonight on the YouTube stream, has said that it reminds her of a view through a kaleidoscope, which is definitely possible. And if anyone's got any better ideas, write them in the chat. You can chat all the way through. Please feel free. We'll be chatting to people on there. If you have any questions for Dr. Luke, anytime during the show, put them in the chat and we'll get to them at the end. So start thinking about your hard science questions right now. So, Dr. Luke, are you ready to wow us with some astronomy tonight?
I think so, Greg. I think so.
I love your enthusiasm. Now,
yeah, I'll kick in.
So take it away, Dr. Luke.
Okay, so as I briefly mentioned before, I'm going to talk to you tonight or this morning or this afternoon, wherever you are in the world, about some of the things that I find personally amazing about astronomy. Now, there are tons and tons of things in astronomy which will completely blow your mind. I'm only going to talk about a few things today, and they're things that I've cherry-picked. So the things that I find that get me excited about astronomy and will hopefully get you excited too. Now, I want to say before I start, this talk is kind of aimed at a lower high school audience, but I'm hoping that everyone can get everything out of it as well. But I'm really keen the idea that there's hopefully some children of that age out there who this will get them excited in astronomy, and then they'll want to go on and do astronomy for their future career, because I can tell you it's a pretty good job to have. And I'll hopefully convince you through this talk that you should be as excited as astronomy is about as I am as well. So the first thing on my list of amazing things in astronomy is stars. So what is a star? Well, this is in fact our nearest star to us, which is the sun. So you see the sun every day, and the sun is exactly the same as every other star that you see in the universe, in the night sky. When you look up, it's just much, much closer to us than every other star in the sky. And we can see loads of interesting things going on in the sun. This is the sun viewed through a filter. I hope I don't have to say, but don't go outside and look at the sun. It won't look anything like this, and it will hurt you a lot. But this is what the sun looks like when you look through a particular filter in a telescope, and you can see lots of things going on, like there's a big flare that pops out of the one corner, and you can see different colored regions, and those are actually different temperatures on the surface of the sun. And this number at the top, this huge number, which some young kid actually pointed out to me in a talk, is a septillion apparently, and I didn't actually know, and they told me what it was, which was great. That's the estimated number of stars in the universe. Now, we can't see all of these stars. What we do is we look at all of the galaxies we can see, and I'll talk about galaxies in a little bit. And we estimate how many stars are in each galaxy, and we add all of those up, and we get to this number of an estimate for how many stars there are in the universe. So this is the sun. The one thing I have to tell you about stars is that stars, in fact, are actually just incredibly boring. The only thing that's actually exciting about a star is when it dies. So stars can die in really, really cool ways, and I'm just going to point out 3 really exciting ways that a star can die. So what are these exciting ways? Well, the first way is that a star can die in a supernovae. Now, a supernovae is basically just a massive explosion. What happens is the star all the time is creating energy, and what it does is it takes hydrogen essentially and it crushes it together and it releases energy, and that's the brightness you can see of the star. Now, certain types of star, when they actually run out of their hydrogen fuel in the center, will collapse down on themselves and then explode in this massive explosion that's the supernovae. Now, these supernovae are so big, they have the energy of this 2000 billion atom bombs. So they're huge explosions, and they're so big that you can actually see them right on the other side of the universe from the Earth. Now, this pretty image you can see here, it looks like a simulation or something, but this is an actual real observation of what's left over when one of these stars explodes as a supernovae. So this is, you can think of the debris of the star once it's blown up and exploded all of its stuff out into space. The second way that's exciting that a star can die is something called a neutron star. Now, in a much bigger star than one of the ones that goes supernovae, when the star runs out of its fuel in the center, instead of blowing up, it actually collapses down on itself, and it gets smaller and smaller and smaller and denser and denser and denser until all of the material of the star is crushed down into a very, very small region. And it's so dense that if you had a single teaspoon of what was left, it would weigh about 100 million tons. So a tiny teaspoon in your hand weighing 100 million tons. Now, these things actually rotate round very, 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 very fast, and they spin and they shoot out jets of energy from their poles. So this isn't an actual image. This is a artist's impression of what this might look like. And they fire this energy out of their poles. And those poles spin round like lighthouses shining through the universe in beams. And we can see those on the Earth. There's things called pulsars as the beams of light fly past us all of the time. And then the final way that a star can die that's exciting is in something called a black hole. So some stars that are really big, when they collapse in on themselves in the same way that a neutron star does, they keep collapsing down even more and become even denser than what you'd have in that teaspoon. And they get so, so dense that they actually essentially break the laws of physics in the center. What happens is that all of the laws of physics fall apart because things are too dense, and you have this thing called a black hole, which we don't really know much about what happens in the center of a black hole because nobody can really see down into the center, and we don't really know what goes on with the laws of physics. Now, these black holes are so dense that actually light is sucked into them by gravity, and that's why they're called black holes. So if you shine a beam of light and it goes close to a black hole, it will get sucked in, and that's why we can never see them. So we know black holes are there because we can actually see stuff spinning around them, outside of them, but we can't actually see the center of the black hole because no light can escape from it. So stars are an amazing thing in astronomy, but personally, I think they're pretty boring when they're alive, and they're only really cool when they die in these things like supernovae, neutron stars, or black holes. Okay, so what's next on my list of amazing things? Next is life on other worlds. So we're in a really exciting time in astronomy in this field, because essentially we may really be on the precipice of just starting to detect whether there is signatures of life on other planets. And to go back about sort of 20, 30 years, we didn't really know much about this at all. We didn't know about many planets outside of the ones in the solar system. And we're now starting to be able to potentially detect that life's there. So I'll try and explain to you how we go about doing that. So the first thing you need to do if you want to find life on other worlds is actually find a planet. So how do you go about finding a planet that's around another star? Well, there are two methods that we use to do this. The first one is something called a transit. Now, what this means is that when the planet's going around the star, the planet passes between us and the star and actually blocks out some of the light from the star so we can't see it, and you can actually measure that. So here I have my star, which you might see as that image of the sun I had before, but it's not the sun, it's the star somewhere else. And I have a planet, and when that planet passes in front of the star, the amount of light that I'm showing you on the bottom right dips a little bit. So all that's happening is that we measure the light from the star when there's no planet, and then when the planet passes in front of it, we measure a bit less light. And you can actually work out from the shape of the light that you see from the star how the orbital period of the planet, so how long it takes the planet to go around the star, which is essentially like a year for the Earth. And you can also tell by how big the dip is, how big the planet is. So by looking at lots of stars and measuring how their light changes with time, we can actually measure planets going around those stars, how big they are, and how long they take to go around the planet. And this teaches us about what the planet's made of and its composition. The second, this has been done relatively recently in lots of different ways. And you may have heard in the news, there was a very famous system called the TRAPPIST system, which NASA detected a few years ago. And this actually has, I think it's 6 planets all going around their star, and they're all detected in this way. So this is actually a video from NASA showing you the actual data that was collected. And can you see that on those dots at the bottom, there's loads of dips going down? That's actually a dip in the light from the star when the planet is blocking out its light. So this is real data that's been used by NASA to detect planets that are going around other stars using this method. The next method we can use is something that uses the velocity of the star, and that's essentially how fast the star is moving towards and away from us, and it basically measures a star's wobble. So this is kind of like a hula hoop. So here we've got Darth Vader in the bottom corner doing his hula hoop, and what's happening is that Darth Vader moves slightly in the middle, and the hula hoop moves a lot around the outside. So when the planet's moving around the star wiggles like Darth Vader does. And we can measure that wiggle in the star and work out about the planet. So here at the top, I'm showing you the distance to the star, and we have our star with our planet going around it. And as the planet moves around the star, the distance to the star that we measure changes slightly periodically over time, and it forms this wavy pattern, like a sinusoidal wave. And we can actually use the shape of this wavy pattern to measure, once again, how long it takes the planet to orbit around the star, and also how big the planet is. So using these two methods, we can detect lots of planets around different stars all throughout our galaxy. So the next question is, we have all of these planets, how do we go about detecting if there's life there? So the way that we do this is we use something that's called the Goldilocks Zone. And the Goldilocks Zone just says that that planet is about right for life. Now, how do we know if it's about right for life? Well, the thing that we look for is essentially just liquid water. Now, we don't know that life in the universe anywhere else actually needs liquid water to live at all. However, on Earth, we find that everything does need liquid water that's alive. So we think maybe if life is like it is on the Earth, somewhere else in the universe, it might need liquid water as well. We don't know that for a fact, but it's the best kind of guess that we can have. So how do you work out if a planet has liquid water? So what I'm showing you here is a figure that shows on the bottom axis the distance that a planet is from its star, and then on the y-axis is the temperature of the star. Now this band that I'm showing you down the middle is this Goldilocks zone. So this is essentially the region where you might be able to have liquid water. And all this means is that the temperature of the planet is between 0 degrees and 100 degrees. So anything that's closer in than that is too hot for liquid water, and the water would evaporate. Anything that's colder than that is too cold for liquid water, and you get ice. And this Goldilocks zone in the middle is just right. Now, as you have the planets that are plotted that are in our solar system currently. Now, luckily, you can see that the Earth sits in the middle of that. And the planets that we have there, luckily, the Earth is just right in the middle. So we have liquid water. And that's great because we know that we have life here. You might be interested to see that Mars actually sits just inside of the Goldilocks zone. So we think that Mars at some point in its lifetime may have actually had liquid water as well. And that's why lots of people go to be able to try and find if there's life on Mars, because it does just about sit in this Goldilocks zone. Now, as you can see here, there's lots of other planets that sit in this Goldilocks zone, which are the ones that we've detected around other stars. So these are all really good candidates for actually finding life on those planets. And if I overplot on here this TRAPPIST system that I talked about before, you can see here that a number of the stars in the TRAPPIST system actually sit within the Goldilocks zone. So they're potentially places where there might be life outside of our solar system. Now, we haven't detected life on these planets yet, and we're just, as I mentioned, on the sort of early stages of being able to potentially find life on those planets. So how do we go about finding life once we have a planet that we know is in the Goldilocks zone? Well, there's a method for doing this as well. And the way we do it is by looking at the light that comes from the star. So here we are on the Earth, and we have a star that's some distance away. This is obviously not drawn to scale. This star is very, very far away from us. And we can look at the light that comes to us from that star. What we can do is we can then split up that light into its component wavelengths. Now, what does that mean? Well, that basically means that we take a rainbow of the light. So we can shine it through something like a prism, and we can split that light up into the amount of light that we get at different colors. So what I'm showing you at the bottom is the wavelength of light, which is essentially the color, against the amount of light that we see from the star. Now, this might look something like this jaggedy line here, where you get slightly different amounts of light at slightly different wavelengths. What we can then do is we can wait until the planet that's going around the star gets in the way between us and the star. And we can do the exact same thing again. So we do that with our planet in the way. Some of the light will come from the star and actually pass through the atmosphere of the planet before it reaches us. And once we do that again, we find that the shape of the light that comes from the star is actually slightly different. We might see these regions where you get a lot less light at particular wavelengths or colors. Now, these patches where you get a lot less light can actually be associated with different elements within the atmosphere of the planet. So potentially you might look at a planet that has this signature and say, oh, look, there's water there, because those specific lines only correspond to water. And you might look at a different planet and do the exact same thing and find that there's different lines in the amount of light that you see. And potentially that could be something like methane, which we know is produced from animals when they eat, like our cow here, producing a lot of methane. So if we look at planets that we've found through our transit method that are going around other stars, and we look at the light that's passing through their atmospheres when they reach us, we might find these signatures of elements in their atmosphere which are associated with life. So we're just about doing this now. The first results of actually using this technique to try and detect signatures of life on different planets have actually just started. So we're right on the verge of being able to potentially find these things. Now, this doesn't say that there's life definitely there, and this isn't actually going and talking to aliens in any way or communicating with them or them coming here. This is just finding elements in the atmospheres of these planets that might suggest that there's life there. Okay, so stars. Boring, exciting when they die. Life on other worlds just kicking off. We're on the verge of being able to detect these signatures. Next, I'm going to talk about galaxies. Now, galaxies are obviously the most important thing in this talk because they're the thing that I study in my day-to-day job. So I'm going to talk a little bit about them and why I think they're exciting and why I bother working on them. So when I give this talk to lots of school kids, I actually have my next slide being a question of what does the Milky Way look like? And I will answer you the question that people usually give me in that talk, and they say it looks like a spiral. And I say, oh, that's nice. The Milky Way looks like a spiral. And then I say to them, well, how do you know? And people will say, well, I've seen a picture of it. And I'm like, have you seen a picture of the Milky Way looking like a spiral? Because I don't think you have. And then I say, oh, well, the Milky Way actually looks like this. This is what the Milky Way looks like from the Earth. It's a band of sort of cloudy stuff across the sky. Now, this is the photo taken in Australia where you can see the Milky Way really, really well. If anyone is listening from the Northern Hemisphere, I apologize because you don't get to see the Milky Way very nicely. I grew up there as well, and I never got to see it. And I came to Australia and it looked like this, and it's completely amazing. Now, when people said that it was a spiral, they were right. But the only way we know that it's a spiral is that we can infer it from the motions of the stars that we see in this band and by looking at other galaxies in the universe and seeing that they're spirals. So when we look at other galaxies in the universe, they look like this. This is a classical spiral galaxy. We see lots of things like this. And if you look at the motion of the stars that we see nearby us, and we look at other galaxies, we can work out that we live in something like this. Obviously, you can't take a picture of the Milky Way because you can't go outside of it and look backwards and take one. But we see lots of galaxies that are spirals, and the stars' motion make us think that we live in a spiral galaxy as well. We can work out that we live roughly about here within our spiral galaxy, about 2/3 of the way out of the center in one of these spiral arms. Now, you might think that you're sitting pretty still at the moment. You're probably just chilling out in your house, sat in front of your computer screen, listening to me talk, but you're actually at this moment flying at about 300 kilometers per second through space. You're going faster than a bullet right now, spinning around this galaxy. So this galaxy is a spiral. You can think of like a plate, and this plate is spinning around really, really fast, and you're spinning around with it all the time. Now, it takes a few 100 million years for us to do one rotation of the galaxy. So where you are right now, the last time the Earth was in this place in the galaxy, dinosaurs roamed the Earth. So that's our galaxy. Our galaxy is really interesting, but what you find is the universe in a whole is actually completely full of galaxies every single place that you look. So what I'm showing you here is a picture that comes from the Hubble Space Telescope that you may have heard of, which is one of the most impressive telescopes that humanity's ever built, that sits in the atmosphere, and it allows it to take really, really clear pictures of space. And this is something called the Hubble Ultra Deep Field. So this is actually the deepest image, or the faintest galaxies that humanity has ever taken a picture of, essentially. And what this is that the Hubble Space Telescope has looked at the same patch of sky for a very, very, very long time, and then added up all of the light that it's collected over that time and produced one image from this. Now, in this image, the size of this image is about the same size as the little red box in the left-hand corner in comparison to the moon. So if you look up and you see the moon in the night sky, that's how big this image is in comparison to the moon. Now, you can see that there's lots and lots of points of light in this image. If you were to look at that patch of sky with your eyes in the night, it would actually be completely black, completely empty. You'd see nothing at all. It was actually chosen by the Hubble Space Telescope to be one of the darkest points in the night sky that you could actually see. But when Hubble looks at it for a very long time, you actually see all of these points of light. Now, every single point of light that you see on this image, except for a few, you can see a few that have crosses on them. Those things are stars, but everything else that doesn't have a cross on it is a galaxy. Each one of those galaxies actually contains billions of stars. So there are billions and billions and billions of stars just in this one single image of space. And there are thousands and thousands of galaxies. Now, this isn't a unique region of the sky. If Hubble looked at any patch of the sky, and the entire sky that we could see, it would see the exact same thing. And you can see interesting things like the galaxies all look different. You can see blue ones that look like spirals. You can see red ones that look like spirals. You can see red, clumpy, oval, rugby ball shaped things. You can see greeny things. You can see white things. And these are all different types of galaxies. And we can learn about those galaxies and what they're like, and actually work out how they interact with each other, how they form stars, how they change with time. And that's what I do in my job. Okay, so that's galaxies. Next, I want to talk to you about the size of the universe. Now, this is a really hard concept to get your head around. And this is the thing that in astronomy, when I started doing astronomy, really completely blew my mind. And I didn't really know how to get my head around it. So it's very complicated, but it's really impressive when you actually work out how it all works. So in order to measure something like the size of the universe, you can't use like centimeters or meters or even kilometers or miles, because the sizes are just so big, it just doesn't really make sense. So we have to use something else. And what we use is something called a light year. So a light year is essentially not a measure of time, even though it's got year in it. It's actually a measure of distance. So a light year is essentially how far light will travel in one single year. So just to try and explain that, if you look at the sun and the earth, a photon of light that leaves the sun and comes to the earth takes about 8 minutes to reach us from the sun. So if the sun suddenly stopped shining one day, we wouldn't know about it for a whole 8 minutes. Things would get very, 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 very bad after those 8 minutes, but we'd be quite happy for 8 minutes. Don't worry, it's not going to happen anytime soon. But in those 8 minutes, that's how long it takes light to travel the distance through space from the sun to us. Just to put that in context, if you wanted to drive there at a normal-ish speed, it would take you about 170 years to drive from the Earth to the sun. So light goes really fast. Now imagine that I have a star that's 1 light year away from the Earth, and there actually isn't even a star that close to us. Now light leaves that star, and it travels through space. And you go to school, and you start your new year, and you have all your classes, and you do your exams, and you go back round, and you have Christmas, and you have your holidays, and then you start back to school the next year again. And in all that time, that light has been traveling through space, and then it finally reaches us. So that's 1 light year. So that's a really, really long distance. It would take you about 65,000 years to drive 1 light year. So it's a very long time, and I don't recommend trying to do that. Just to put this in more of a context of things that you might know about, for anyone in Australia, the distance from Perth to Sydney, all across Australia, is about 0.000, lots and lots of zeros, 42 light years. So light travels across Australia incredibly fast. Let's go bigger and see if that makes more sense. What about the circumference of the Earth? So once around the Earth is about 10 times bigger, so we're still in a tiny amount of light years. What about from the sun to the Earth? Well, we've talked about that before, but to show that in the opposite way around, this is about 0.000158 light years. So it's still a tiny, tiny measure of light years. Let's go bigger again. What about the solar system? So the whole solar system is actually about 1 light day. So light takes about a day to go from the sun all the way out to the edge of the solar system. And we're starting to get into sensible-ish slightly terms where you might want to use light years to describe a distance. Kilometers and things are completely blown out of the water now. You don't want to use those because you just end up having tons and tons of zeros. What about the nearest star to us? So the nearest star to us is actually a binary system called Alpha Proxima Centauri, and they're about 42 light years away. So light from the nearest star to us in the entire universe takes about 4 years to reach us. What about the size of our galaxy? So the Milky Way galaxy that we showed before, that's about 100,000 light years across. So just to put that in context, if there were aliens and they lived on the opposite side of the galaxy to us, if they wanted to send a signal to us, to talk to us, it would take 100,000 years for their message just to reach us, and another 100,000 years for the message just to go back. So if you put that in context, humanity's only really had the ability to send out signals into space for about sort of 150 to 100 years. So we've not been able to send signals to anywhere near any distance without in our galaxy. So it's very, very difficult to actually communicate across the cosmos because the speed of light is a really limiting factor, meaning that we can only actually communicate with parts of the universe which are very, very close to us. Let's go even bigger again. What about the nearest galaxy to us? So the nearest galaxy to us is the Andromeda galaxy. The Milky Way galaxy and the Andromeda galaxy are actually hurtling towards each other very, very quickly. And at some point in the far future, they would actually merge together to form one much bigger galaxy. The Andromeda galaxy is about 2.5 million light years away. So when you look up into the night sky, if you can see the Andromeda galaxy, you're not seeing the Andromeda galaxy as it is now. You're seeing the Andromeda galaxy as it was 2.5 million years ago, before humans even existed. So you're looking back into the past as you look out into space, because the galaxies are so far away that it takes such a long time for the light to reach us. Let's keep going bigger. Next, you can go to clusters of galaxies. So this is lots of galaxies clumped together, and they're about 32 million light years across. We can go even bigger again and get to silly numbers of light years now and talk about the most distant galaxies that humans have ever detected. And they're about 350,000 million light years away, which is a massive number, which I can't even get out. And you have to say now because the universe is expanding, and you have to quantify a time when you talk about these distances, because things get really complicated when you go on big scales. And then you can also go to the biggest scale possible that we could measure. And this is the size of the observable universe. Now, this is actually basically means how far we could actually see during the whole lifetime of the universe. So there are regions outside of this in the universe where the universe hasn't been alive for long enough for the light to actually reach us. That's how big the universe is. There are parts of it that in 13.7 billion years that the universe has existed, light hasn't had the time to reach us. So this is the biggest that we could possibly ever see. Now, to put this into context again, light from the most distant galaxies that we know about has traveled this huge number of trips from Perth to Sydney. And if you were allowed to travel at the moment, you would rack up some serious air miles by doing that. But I don't recommend that one as well. So as I mentioned previously, because the light takes so much time to reach, so long to reach us from these galaxies, the further we look out into space, the further we actually see back in time. So this actually gives us a really unique perspective on the universe. The further away a galaxy is, the further we're looking back into that galaxy's past. So if I look at different distances away from me, I can actually see what galaxies were like earlier in the universe. And the further I look away, the earlier I see those galaxies. So this allows us to do something called galaxy evolution. And this is basically what I do in my day job. So just like in measuring evolution on Earth, you have our paleontologist here who digs up a fossil and they study that fossil and they try and understand how it works. And our astronomer over here looks at a galaxy in the distant universe and tries to understand how that galaxy works. Our paleontologist then digs up a different fossil and suggests that that fossil might be from some time later and tries to draw this evolutionary link between the two fossils that they've discovered. And the astronomer does the same thing. They look at a galaxy that's closer by and therefore exists later in the universe and try and pieces some evolutionary link between those two galaxies. And this is what I try and do. So here I've got a video showing you kind of how this works. You get stars forming in the early universe, which then all clump together to form galaxies. These galaxies then all smash together to form different galaxies over time. And then ultimately those bigger galaxies will smash into each other to form very massive things that we see today in the universe. And this process of galaxy evolution and galaxies changing with time ultimately leads to tons and tons of different types of galaxies that we see in the nearby universe. And these are all these amazing types of things that you can see. And I try and study all of these galaxies and try and work out how they formed and why they all look different from each other. Okay, so we've been through stars, boring, exciting when they die, finding life on other planets and how we might be just about to be able to do it. We've talked about galaxies and the Milky Way and how you're flying through space really fast right now. We talked about the size of the universe and how it blows your mind. And then finally, we talked about galaxy evolution and how you can study how galaxies change with time. So I'd like to end a bit by asking the question, well, why is the cosmos really amazing? And it's actually not because of any of the things that I've told you already. The reason that the cosmos and astronomy is really amazing is actually because we don't know much about it at all. Things would be boring if we knew everything. And I can tell you from working in astronomy that astronomers know next to nothing about how the universe works. Now, I have my next slide. It was just used to have things on it that we don't know anything about yet. And I used to have this first point that popped up, which was, do gravitational waves exist? And I've been giving this talk for so long that essentially we've now done that. So I have a tick on there because in the time that I've been given this talk, we've actually detected gravitational waves for the first time with detectors that you may have heard of, detecting black holes that merge on the other side of the universe. And we're able to detect those wobbles in space-time that come out as big, huge objects merge. So we're making progress because we're actually ticking off things on my list. But what about the other things that were on my list? Like, why is there anything in the universe at all? Which is a pretty big question. What happened after the Big Bang? What's this stuff called dark matter? How and why is the universe expanding? How do galaxies form? What happens in the black hole? And this list goes on and on and on of things that we don't know about. So the exciting thing about astronomy is we don't know all of these things, and that it's actually for future scientists, like anyone who's young enough to go and have a career in it out there, to find out. So I will be long gone and my career will be over before many of these questions have been asked, but it's people like you that could go out and find the answer to this, to find out what dark matter is, to find out what goes on in a black hole, to find out what happened just after the Big Bang. So I'm sure now after this, everyone is so excited and they all want to go and become astronomers. So I have my final part is just to give you an idea of what you need to do to be an astronomer. So if you want a career in astronomy, what you first need to do is you need to learn to code. Now, we spend a lot of our time sitting in front of computers, writing computer programs. If you can learn to be a coder now, you'll be in good stead because it helps you a lot. I spend most of my time, I would say, writing computer software. The reason for this is because the data that we take, there is actually no software to analyze it. So we actually have to write our own computer programs to work it because it's so far at the forefront of technology that we have to do this ourselves. You have to be inquisitive, so you have to want to ask questions about the universe. You want to understand what's going on, so to be excited about some of the things that I've talked about tonight. And then finally, you just need to go and look up. Like, we're an amazing place in astronomy that to be able to be excited in astronomy, all you have to do really is go outside and look up. You can see stars, you can see galaxies, you can see comets, you can see meteor showers, you can see so many things if you know where to look by going outside and looking up. You can find out where to look online very, very easily. Or I know a few astronomers that you can drop a question to or drop a line and ask about these things. And somebody on these threads will be able to tell you where to look to see interesting things. And then as a tiny sub point at the end, I'll just add that you probably need to study maths and physics as well. But don't worry about that. That's way less important than all of the other things that are above it. So I just want to end with my obligatory slide, which you probably might already have given all of the information that you found your way here. But if you want to know anything more about the things that we do and the things that I do, and you want to ask me a question or anything, here are just some links where you can find out loads and loads of interesting things. I'm very happy for anyone to drop me a line and ask me a question at any time. I won't guarantee that I can answer your question, but I'll try my best to do it. So thank you for listening.
Thank you, Dr. Luke. Amazing. Thank you very much. Now, it is question time, viewers. You can ask any question from Dr. Luke. Ask any question you like, and he will try to answer them. As I said, he may not be able to answer them, but hopefully he'll be able to. But I have a question for him straight off the bat. Of your slide of things that we haven't found out yet, gravitational waves we found out, we had lots of other ones on there, dark matter and the final evolution of the universe, other things. If you could have the secret knowledge dropped into your ear before you died, what's the one thing you'd want to know?
Am I about to die, Greg?
Yes. No. I'm not threatening you. I'm just.
Do I get to share it?
No. That's it. It's just for you. It's
just
only
for me.
Yes. Yep.
I think life existing somewhere else in the universe, actually, I think is probably the most exciting thing. I think the other questions are kind of exciting for people who are interested in astronomy. And they're exciting for me because I study it and I want to know, particularly things like dark matter. I work on some of the things that do that, and we're talking about tests that we can do to work it out. So that's exciting for me, but life on other planets is exciting for everyone, right? It would completely revolutionize our understanding of the universe for everyone on the planet, essentially, if we found out that there was life on another planet or found out what that life was like. So I think I'd like it dropped into my brain, the explicit information about the fact that there may be life on other planets and where it is and what it's like.
And whether it's judging you or not.
Yes, yeah. It's not quite like you, Greg.
So here's a question from the chat. What's your favorite type of galaxy?
Oh, my favorite type of galaxy. I actually really like merging galaxies. So merging galaxies is when you get two galaxies which are in the process of smashing together. So if you take a look or you Google merging galaxies, there's some really cool pictures from the Hubble Space Telescope showing two galaxies which have literally just smashed together. And they look like car crashes. There's just bits flying everywhere. And there's all these streams of stars and material that are all left over when these two galaxies are all crushing together. Now, part of the work that I do is trying to study what happens when these two galaxies smash together and what those events do to the processes that are occurring in the galaxies. But they just make really, really pretty images to look at as well. They're really beautiful. And there's so much like astrophysics going on in those collisions that it gives us really unique things to study. And you can actually learn lots about the galaxies and how they interact and gravity and what goes on with the dark matter and things all through these galaxy collisions. So definitely merging galaxies.
Excellent. So one last question. If you could travel to Mars, would you?
No. I would say that if I was on my own, I would, but I have a 4-month-old baby, and I feel it'd be pretty rude to actually just go away to Mars. and leave them behind. And I think you'd probably not be quite keen to go yet. But if I was single and younger, then definitely, I think it would be awesome.
Fair enough. Fair enough. I'd like to, before we finish up, I'm going to give a shout out to Newbridge School Science for tweeting about this today. And I do believe
that's potentially my the second closest school to me, where I grew up in South Wales. So that's
there you go. So they know you. You're famous. You're so famous. Your old schools starting to know about you. Very exciting.
Oh, sorry.
Luke has no response to that. He's just so humble.
Yeah, I'm so shocked by the Newbury School. I'm just upset that Cwmcarn School, which was my school, was not tweeting about it. But I think Cwmcarn School might have closed down, actually. So maybe not.
You're a hard act to follow, I guess.
Yeah,
so
they said that was enough.